In this video, we're going to look at linear transformations, and a reminder about our notation. We have a function. That's going to be what we define by our f. That's our function. The actual transformation is explicitly done or written out here. This is the actual transformation. But it's not limited to that. In calculus class, we would usually just get away with this, x maps to x squared, or ln of x, or e to the x. But in linear algebra, we need to be a little more specific and emphasize what the sets are that we're mapping to and from. And so we're going to map our S set here, which is called our input set, or the domain. And the elements that are going to come out of the transformation are going to be in set T, and that's often called the output set, or sometimes called the codomain. Notice it's definitely not something we often also called, which is the image. We're going to talk about the image in much more detail, but the set that we're mapping to codomain is the possible space we can end up in. The image is going to be the actual points we get, or vectors that we get. We're now going to focus in on linear functions specifically, and this is going to have some characteristics very similar to the kinds of things we saw with vector spaces, which were linear spaces in some sense. So, linear functions. Imagine we have two vector spaces, and we're going to have a function that maps from one of them to the other, and what we're going to get is something called a linear function if it passes two characteristic tests. So, not too surprisingly, if I add things, then it doesn't matter whether I add the vectors for the input first and then transform them, or I transform the first vector, transform the second vector, and add them when I'm done. Either way is the same, and what that means is that it's safe to swap addition and the transform. I can add first, then transform, or I can transform each first and then add, and that's totally fine. And the same thing is true if I have a scalar multiplier. So I can swap order of a scalar multiplier, scalar multiplication, and the transform. If that's the case, then we have what's called a linear transformation. In a day-to-day use, we often say linear function, linear transformation, linear map, linear mapping. These are all the same thing. So the key word is going to be linear in all of these. It's a linear function, it's a linear transformation, it's a linear map or mapping. So let's start off pretty easy. Let's map the set V to itself. And we're just going to map an element to itself, element by element. And that's called the identity map. It's like x equals x, f of x equals x. And what we're going to show is that this is a linear map. So we're going to test whether L of some vector v, L of v1 plus v2 is equal to L of v1 plus outside L of v2. That's the first criteria for a linear function, so that's what we're going to test. So we're going to consider, and it doesn't matter which way you start, I usually start with this one, the left-hand side. So L of v1 plus v2 for some v1 and v2 that are in our set. So pick any two things in your set. What do we know about this transform? Well, we know that whatever input we get the same output back. That's our particular transform for this problem. So this is literally equal to v1 plus v2 by the definition of L. Alright. Well, that's the definition of L. Now, it might be tempting to try to work backwards from this, but it's honestly safer to look at the other side of this equation separately. So let's call this the left-hand side. That's our left-hand side that we just built. And then we can talk about our right-hand side here and see if they simplify down to the same thing. So the right-hand side is equal to L of v1 plus L of v2, and then again, by the definition of L, when I transform just v1 by itself, I get v1 back. And so, since those two things, the left-hand side equals the right-hand side, L of v equals v passes the first criterion for a linear function. That's probably a few more words than we'd usually write once we've done a few more of these. Usually once we see that these two quantities are the same, we're done. Now we repeat that same basic operation for the scalar multiplication. So we're going to test whether L of alpha v is equal to alpha times L of v. And again, let's call this the left-hand side and the right-hand side. And so the left-hand side, and again, sorry, I should put the extra ingredients here for alpha being a real and v being some element of our vector space v. So our left-hand side here is L of alpha v, which is equal to, well, the transform by the definition of L. Our specific L in this case takes any input and just gives you the same output back. It's going to be alpha v. Meanwhile, the right-hand side of that equation that we're considering is alpha times L of v, and again, by the definition of L. This time I just have L of v, but L of v is just v by itself. We're going to get alpha v, and since the left-hand side equals the right-hand side, L of v equals v passes the second criterion, 2, and both of those together means that L of v equaling v is a linear transform or linear function. Not the most exciting example, I will fully agree with that. The key thing is to look for the criteria, how you express that, and then how you might sketch out a sequence of transformations that show the two quantities that you need to show are equal, either through the sum being the input, or taking the sum after the transform, or the scalar multiplication before and after the transform as well. Now let's take a quick look at an example where it is probably not linear. We have the absolute value function here and the square root. The absolute value is to guarantee that every input has a valid output, which is one of the requirements for our linear algebra definitions of functions. But with that, we're fine. So what we can do is note that we expect, because there's a square root, right? We expect this not to be linear. All right. So we're going to try to build a counterexample. Counterexample too, not a counterexample. Counterexample to, let's do this sum first. So L of v1 plus v2 equals L of v1 plus L of v2. Right. So e.g., let's let v1 be square root, something nice to square it. Let's say 4, and let's make v2 equal 9. Right? Then the left-hand side of this equation up here is the L of v1 plus v2, which is the L of, do the sum first, so 4 plus 9 inside the brackets. 4 plus 9 is 13, so L of 13, which is the square root of 13 by the definition of our function. Meanwhile, the right-hand side, which is L of v1 plus, oops, careful, close bracket, and then plus, and then L of v2. That's L of 4 first plus L of 9 next. Well, that's the square root of 4 plus the square root of 9, which is 2 plus 3, which is 5. But the square root of 13 is not equal to 5. And so, just by that one counterexample, L of x equaling the square root of the absolute value of x is not a linear function. As soon as we have one failure on one example, we're good to go. Proving the general case is usually, it's more abstract, more general, but to prove something's not true, we just need one demonstration of it. Now, a third example here, determine whether this function is a linear transformation or not, and here's where we get a distinction between calculus and linear algebra, as we will see. So you might think this is linear, but we're going to try some values and see what happens. Let's let x's, so let's let x1 equal 1 and x2 equal 3. And then we're going to consider the test or the requirement. Let's call it this way. Say the requirement is that L of x1 plus x2 calculated inside the L and then transformed should be the same as the transform of x1 first and then x2. That's a requirement. The left-hand side here for our particular values is the transform of 1 plus 3, which is the transform of 4, which is 3 times 4 plus 1, which is 12 plus 1 is 13. While the right-hand side is L of x1, which is 1, plus L of x2, which is L of 3. So we're doing this calculation here, and here we can see the snag. When I transform the value 1, I'm going to get 3 times 1 plus 1, all that in brackets. And then to that, I'm going to add the transform of 3, which is 3 times 3 plus 1. And you see what happened? Here I have 2 plus 1s. This plus 1 is a bit of an issue. We're going to get 4 plus 10, which is 14. And since 13 is not the same as 14, we fail this test. This L fails this criterion, specifically this linearity criterion, which means that L of x equals 3x plus 1 is not a linear function. It's not a linear function in linear algebra class. Now, in calculus, we're going to continue to call this a linear function because it has a constant slope and these other things, but we remember that the 0 value is special in linear algebra, and this plus 1 here kind of ruins that. If we had a function that was just 3 times x, that would turn out to be linear. Technically, this is what's called an affine function, but again, in common parlance, in a calculus class, we would just call this linear, but in linear algebra, no. This function with this plus 1 on the end or plus anything else, the shift, is not going to be what we define as a linear function with the rules, the more precise rules we're using here. And that's an important distinction to have in mind.